Hi, my name is Dr. Ken Tindall and I am the CTO of Canis Automotive Labs. You can see my email address here, and if you have any questions at the end of this, then feel free to email me. Right, before I start the rest of the talk about the CAN security add-on layer, I want to talk about CAN security in general. There are many different threats to a CAN bus. Some of them are remote attacks on a CAN bus that have maybe come over the internet. Some of them are local attacks that come through something connected to CAN that also has a Wi-Fi or Bluetooth interface. And there are wired attacks where someone is able to break into the CAN bus at the physical layer. And when they get access to CAN, there are many different types of CAN attack. So one example is a confidentiality attack where someone can sniff the CAN bus and pick up important, perhaps personally sensitive information. Another is an integrity attack. For example, someone attacking can spoof a CAN frame as if it came from some other device in order to make a system do something that it shouldn't do. And there are availability attacks. So for example, the CAN bus can be made unavailable by flooding the bus with CAN frames that shouldn't be sent on the bus at that rate, slowing it down and causing all the real-time functions to miss their deadlines. And as well as ordinary frame attacks where you see CAN frames on the bus, there are low-level attacks on the CAN bus at the very protocol level itself. For example, the bus off attack is able to spot the identifier part of a CAN frame, know that it's coming from a targeted device, and then destroys the CAN frame before it's finished, causing the transmit error counter on the targeted device to go up. And by repeating that attack multiple times, you can force a particular device to go bus off and be disconnected from the CAN bus. And there are several ways to defend a CAN bus from these attacks. So a classic approach is to have an intrusion detection system that listens to the bus and looks for something unusual going on and can then flag an attack that's happening. There are CAN security gateways that will take a trusted side and an untrusted side and pass traffic back and forwards, but only if it meets certain criteria, so then it becomes impossible to do certain things like spoof frames. There are hardware defenses. So for example, NXP has a secure transceiver called the Stinger that knows what's going on for its local device and will destroy CAN frames that are behaving incorrectly, so an attempted spoof attack by that device. And Canis Labs' own CAN-HG hardware will do a similar thing using intrusion detection prevention system to destroy spoof messages. And there are encryption techniques where information can be hidden and authenticated so that only legitimate transmitters and receivers can exchange secured messages. And that's what I want to talk about today. For these other techniques, for more on that, see there's a 4-part Defending CAN video series. And if you just type Defending CAN bus into a search engine, you'll get access to those videos on YouTube. Now, if we look at encryption, it's absolutely a required defensive technique to stop physical wire attacks. So wired attacks are made when an attacker has a connection to CAN bus by breaking into a system, attaching to the CAN high-low lines of the twisted pair, and then sending CAN frames into the system to spoof them. One of the things a wired attacker can do is go beyond the normal CAN physical layer and actually modify the electronics. So it's possible to create modified CAN transceivers that are able to drive the bus to a recessive state and suppress error frames from anything trying to defend. And it's worth saying that CAN injection, which is a wired attack where you inject these frames, is rapidly becoming a common technique for vehicle theft. So for example, here is a report on the Times on the left of a stolen car from, in fact, a friend of mine in Tabor, who's an automotive cybersecurity researcher. Thieves came back to his car and cracked in through the headlight and injected CAN frames onto the CAN bus, deactivated the immobilizer, and drove his car away. And in the photograph on the right shows an attack on a car where the body panel has been broken into to get access to the CAN bus. So wired attacks are becoming a real problem in the automotive industry. So if we look at encryption on CAN, Canis Labs has come up with a scheme called CryptoCAN. And it's an add-on security layer that turns any given CAN frame into a protected CAN frame. And that protection is encryption, so the CAN payload of the original frame is kept secret, and it's authenticated. So it proves with an authentication code that the CAN frame came from a legitimate sender. Now, it's worth pointing out here that all cryptographic schemes have some issues. For example, they do not prevent denial of service attacks. So if you're trying to defend against an availability attack on the CAN bus from things like CAN bus flooding or CAN protocol attacks, encryption doesn't actually help very much here. They all need key management because each system has to have a different set of keys. Because if you don't do that, then an attacker who can break into one system can then extract the keys and break into them all with no effort. And for example, all suffer from potentially replay attacks, and that's where an attacker is able to listen to the bus, capture encrypted authenticated traffic, but then replay it later, and because it's a legitimate message that's been captured, get receivers to accept that message. And it's also worth pointing out there are some specific requirements for CAN bus over and above what you normally find for encryption systems. So for example, in this system, in a CAN bus system, a receiver must be able to decode messages if they've gone through, for example, a watchdog reset, or there's been a power glitch and they've gone offline and come back online. They must be able to get up and running really quickly without needing a special dialogue with the transmitter. And that's because CAN is a publish-subscribe communications model, where there may be many subscribers for every single, for any single transmitter. And any single device that publishes something may not know who is subscribing to it. And so there can be no many subscribers trying to talk to and dialogue with each of their own publishers. It's not a feasible technique unless we design the encryption system to handle that. So let's have a quick look at, in essence, what CryptoCAN does. We start with a publisher, and we have multiple subscribers, so it's a 1-to-n system like CAN. And the publisher has a plaintext CAN frame to send, as in any CAN system. And then there is a CryptoCAN encode step. And what that does is that takes the plaintext CAN frame and it produces two ciphertext frames that together encode the original frame and also an authentication code that goes in there. So these are the two protected CAN frames together as a pair make a protective message that implements the plaintext CAN frame. And then at each subscriber there is a decode process, and the decode process operates in reverse. It takes two of these protected CAN frames, a pair in, and turns them back into a plaintext CAN frame. Now CryptoCAN is actually implemented itself is two separate layers. The first layer is a cryptographic layer, and this provides primitives like AES, authentication code generator, algorithms like CMAC, secure random number generator, and so on. It also includes key management, so that means storing the keys so that the application doesn't see their values, and it means being able to update and replace keys using a secure mechanism. And then on top of the cryptographic layer is the CryptoCAN messaging layer, and that does that encode decode functions, and it uses the primitives from the cryptographic layer to do the encoding and decoding. So if we quickly turn to the cryptographic layer, this is normally provided by a hardware security module, and in fact there's a standard for hardware security modules that's been defined by the automotive industry with AUTOSAR that's called secure hardware extensions. And that's available on many microcontrollers you find targeted at automotive. So for example, the NXP S32K microcontrollers, they have a module inside called CSEC that implements this hardware security module specification. Now, if you have a microcontroller that doesn't have a hardware security module, it's possible to get by with a software hardware security module. That's basically an emulation of a hardware security module in software. Now, obviously, that means the software can't run as fast as a real hardware security module, and it's not storing the keys securely. It's storing them in local non-volatile memory, and the host software could investigate and find out those keys if it had some infected with malware. But nevertheless, it means that someone purely from watching from the bus side in a wired attack, it's functionally the same as a hardware security module, except for performance. And in fact, Canis Labs has built a software emulation of an SHE hardware security module. And we've in fact taken that implementation in C and wrapped it up into a MicroPython build for our development kits. And there's an API in Python now to be able to play with that. And you can see it's pretty efficient. So the AES basic encryption operation takes 20 microseconds, and that's on a tiny Cortex M0 running at 133 megahertz. And in code space terms, it's about 3K, 2K for Decode, and then another K for a table, and it's about 200 bytes of RAM. So it's a very small implementation that runs pretty fast, that can be used instead of a hardware security module if the microcontroller doesn't have it. So if we go back to the CryptoCAN messaging layer, that uses some of these core HSM functions. So it uses AES encrypt, but CryptoCAN doesn't use decrypt because of the particular mode of encryption it uses to protect the frames. You can actually skip all of the overheads of the decrypt code being present. It uses message authentication code generate and verify. These are two standard SHE operations in a hardware security module. And it uses random number generators. So these are the functions together that are normally in the HSM that CryptoCAN uses. It's very small, so the Canis Labs implementation of the messaging layer is about a kilobyte of code space, and it takes about 40 bytes for a RAM for each CryptoCAN frame source. So that's called a context. So any given repetitive sending of a CAN frame, that's a single context required to decode each sending of that CAN frame. And it's pretty fast. It adds only a couple of microseconds to the basic encode or decode operations that the HSM takes. So basically for creating a pair or decoding a pair, that's the equivalent of 2 AES operations. And each of those are about 20 microseconds in our software implementation. So we've been talking about message authentication a little bit so far. It's important to dive in a bit in detail here about exactly how that works. Message authentication requires a separate key from the encryption key. That's in order to avoid certain weaknesses in the encryption algorithm if you try and share keys. And the SHE standard for hardware security modules has a permissions scheme so that a key can be defined as an authentication key or an encryption key, but it can't be used for both. And that's to protect against this weakness. Now that generates a message authentication code, and that proves that the message is legitimate. And by legitimate, I mean it must have been created by a device that knew the MAC key. So a subscriber knows the key, obviously, because it does the same MAC calculation that the sender does in order to verify that the message hasn't been tampered with. And that would normally mean that a subscriber could then generate spoof messages because they have a copy of the key. So any subscriber could generate spoofs. So this has been recognized in the SHE standard. There's an augmentation called SHE Plus, and that adds an extra permission for generate. So you can define an authentication key that has a generate permission or a verify permission. So this means that a subscriber that's doing verification of an authentication code can't then generate them. because the applications can't see those keys. Now, the second important thing about message authentication is that a legitimate message must also be recent. I mentioned before how encryption schemes suffer from weakness of replay attacks, where an attacker can sniff around, capture a message, and then replay it later. And because it's legitimate, it can be accepted by receivers. So part of the way the authentication code needs to be computed is it needs to be include some measure of how recent that message is, so that old messages can be discarded and will never verify. So that brings us to freshness. So the calculation of a MAC must include a freshness value, and that indicates when the message was generated, so that all old messages won't verify because their freshness values are too old. Now, the receivers should know the freshness value that was used to create the message, and then must use it themselves in the MAC calculation. Because if a different freshness value is used, then the MAC calculations will produce different results and won't match, and then the frame can be rejected. Now, the freshness value is a potentially application dependent system. So, for example, a freshness value could include a network timestamp. So it might be a network clock that's being distributed everywhere, and that is used as part of the MAC calculation. Or it might be a sequence number that a particular device is using, and it just increments its sequence number every time it generates a message. Or it could include even some of the bits of the freshness value, could include something like a boot count, a measure of how often or when the system has been rebooted, and a count of how many times that started, so that every time the system starts up again, all previous messages no longer can be validated as fresh, because the part of the boot sequence has incremented a counter, it's stored it in non-volatile memory, and this protects against this replay attack. So CryptoCAN, because of the way there's different ways of interpreting and creating a freshness value, CryptoCAN includes a freshness value in the API, but it doesn't define the semantics of that. Because it's this application-specific value, it's very often linked to network management to do with devices going offline, coming back online. So it's left to the application to decide exactly what semantics to apply to a freshness value. So if we go back to our encode decode and then take a little bit more of a look at the details of this. We take from the plain text the payload and the DLC field, the length of the payload. We also take in the CAN ID and this freshness value, and then with the MAC key we compute a message authentication code and then add that into the data that's sent. And in CryptoCAN that adds up to 128 bits. And that can't be carried in one CAN frame, of course, so that's split into 2 CAN frames. And then that 128-bit block is run through with its previous ciphertext value, the encryption key, and that gives us the total ciphertext. So we produce a plaintext payload DLC and MAC code, and then we encrypt the whole lot with a factor from the previous ciphertext. And that gets sent on the CAN bus. And then on the decode side, the reverse process applies. We take the previous ciphertext and the encryption key, and that gives us back our payload, DLC, and MAC, our plaintext. But we can't pass that up yet because we haven't verified the MAC address. So we do the same calculations with the CAN ID and freshness and the MAC key, and because they're the same at both ends, that gives us a MAC, calculated MAC. And if nobody has tampered with the message and the freshness values are the same, then that will match. And then we know that this is a valid, legitimate frame, and we can pass it up to the application. So you can see here what goes in is a CAN frame, then there is this magic process of authenticating and encrypting it, and then at the other end what pops out again in the reverse process is back to our plaintext CAN frame. Now there's an issue if a freshness value is used from a timer, a global time like we talked about, or some kind of synchronized timer, because the freshness value has to be used at the publisher, the same value known at the publisher and subscriber. And if the freshness value is a timestamp that came from a shared timer that was across the network, this can be an issue because the time the message is created is different to the time the message is received. So the verification will fail if the receiver freshness value is used at the receive time. So CryptoCAN provides an option to address this that exploits a nice little feature of the CAN protocol, that if you have 8-byte frames, and all the frames in this CryptoCAN, the pairs are each 8 bytes, then the bottom 3 bits of a DLC is ignored by the CAN protocol because they're all 8 bytes, and any value between 8 and 15 is still 8 bytes. So those extra bits can be used, 3 bits for frame A and 3 bits for frame B of the pair, giving 6 bits. What we use in CryptoCAN is optionally, we can take the bottom 6 bits of the freshness value, if it came from a timer, and put them into that AB pair of frames. And then when they get received at the other end, the timer will be different because of the time taken to go into the CAN queues, win arbitration, and be sent. But the 6 bits tell us enough information to back calculate from the current freshness value from the timer to the original freshness value used to send the CAN frame. And there's a similar little trick we can play that makes it easier use of the freshness value. If we have 11-bit CAN ID systems, we can actually use 29-bit ID frames to carry a freshness value. And we call this the ID enhancement. So it's a scheme, so it has to be an 11-bit CAN ID scheme, for example, CAN open. And we take an 11-bit ID plaintext frame and we create 2 29-bit ID frames. And that means that there are 29 ID bits, only 11 of them are needed to encode the CAN, the original CAN plaintext frame. And so those bottom 18 bits on each pair are used by CryptoCAN. So some of that's used to encode whether it's frame A or B, and then the rest is used to encode a freshness value. And that means the sender can send the freshness value directly on the bus instead of it being an inferred timer or something like that. So we give an extra little option here for device-specific counter, for example. And again, just like we mentioned earlier, this is a network management issue really, because for example we can include our network-wide startup counter into that freshness value, and then if a system crashes and restarts, it can pull back the network time or the network boot count, and then apply the necessary freshness value, so that again very old messages can always be ignored. Just want to talk very briefly about implementing CryptoCAN. The CryptoCAN software we produced has got an API at the bottom into a hardware security module layer. And so you can use any on-chip hardware security module that's available on any microcontroller just by meeting that API with a driver that passes the commands through into the on-chip module. The replay protection I just talked about using the spare DLC bits, that's optional. And the reason there is that in some cases device drivers are buggy and they don't work if the DLC is greater than 8. In fact, some of them contain security vulnerabilities that if the DLC is greater than 8, it causes buffer overflows to happen. Also, it requires that gateways between CAN bus segments have to operate properly. So the gateway mustn't throw away frames and it mustn't reorder frames. The NFTA, the National Motor Freight Transport Association in the US, has been doing some work on this, and they have a specification now of requirements for security gateways, and these are 2 of those major requirements to behave properly. Because if frames are reordered, this can cause a lot of problems, because by reordering the frames, you're effectively tampering with the message content, so they're in the wrong order. So an application will have to resolve those at the application level, or the security gateway has to work properly. Drop frames are similar, that if you drop a frame, you'll be losing a message, and because of the way the encryption works, the subscribers will lose sync, and then the next frame will fail to verify properly. So it's important that gateways behave properly and don't throw things away. So I just have some final remarks before concluding. CryptoCAN needs 2 CAN frames per plaintext CAN frame, and this means there's a bandwidth hit. Fortunately, you don't need CryptoCAN to protect every single CAN frame on the bus, so you can apply this around important messages. So, for example, if it's a vehicle, the immobilizer control and the door locks might be ones you need to protect, and the others less important attractions for a wired attack. Now, CryptoCAN is a high-level end-to-end encryption scheme, so it could be bridged over a local network. So this means the protected messages could be sent from one CAN bus to another, or it means they might come over from a tool that was connected from one bus to another, or a tool that was even in the cloud, and then the messages were encapsulated inside internet UDP packets or something and made their way through to a targeted CAN bus. So it allows some quite interesting uses of this to protect certain messaging from things like external tools. Key management is key in this process. We mentioned this at the start. It's really important. Cryptography causes any problem to be turned into a key management problem, basically. Each device needs its own unique keys, and we need a way of provisioning those keys at the beginning when a system is first set up, and we need ways of storing those keys so that the system can be re-provisioned later. So we need a key management infrastructure, which means a database and tools for reprogramming the keys. And lastly, encryption may not offer very much protection if a device could be hijacked. CryptoCAN is an end-to-end scheme, but if the ends themselves can be compromised by a malware exploiting a remote code execution vulnerability, for example, then messages can be spoofed because it's an end-to-end scheme. If you attack and can control an end, then you can start sending messages because you control the end. So it's important to understand the limitations of encryption on CAN. It's a security technique, but it's by no means the only security techniques that's needed to defend a CAN bus. For further information, I have a white paper that can be downloaded from our website on encryption on CAN bus, and there's also another paper for the GFCETS 22 conference on defending CAN bus that goes into much more detail on how CryptoCAN frames are assembled and created. And if you go to our website, there's a whole section on CryptoCAN, and you can even download MicroPython firmware with CryptoCAN built in that you can run on CAN Pico or even just a standalone Pico W. Thank you very much for listening.